Today we're overclocking and undervolting the AMD Ryzen 9 9950X all the way up to 5.9 GHz. I use Curve Optimizer and Curve Shaper to change the VFT curve of both of the CCDs in this CPU. I provide to you 4 unique overclocking strategies for beginners as well as advanced overclockers. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that I'll be using in this guide. The AMD Ryzen 9 9950X is part of AMD's Zen 5 based Ryzen 9000 desktop processor product line, codenamed Granite Ridge. The Granite Ridge processors were introduced on June 2nd, 2024 during Computex. The Ryzen 9 9950X succeeds the 16-core Zen 4 Ryzen 9 7950X, which we overclocked up to 5.95 GHz in SkatterBencher 44. It has a base clock of 4.3 GHz and a listed boost frequency of up to 5.7 GHz. Just like its predecessor, its TDP is 170 watts. The system we're overclocking today consists of the following hardware. The EFC-SB is a customized version of the original Elmo Labs Easy Fan Controller. It has the same functions and features as the original EFC, with a tiny improvement here and there. The most obvious difference is that this EFC comes in the SkatterBencher color scheme, yellow, white and black. You can support me directly by purchasing an EFC-SB from the Elmo Labs online web store. I use the EFC-SB to monitor the ambient temperature, water temperature and fan duty cycle. I also use the device to map the radiator fan curve to the water temperature. The main takeaway from this configuration is that it gives us a good indicator of whether or not our cooling solution is saturated. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before starting overclocking, we must check the system performance at default settings. The default Precision Boost 2 parameters for the Ryzen 9 9950X are as follows. Here's the benchmark performance at stock. Here's the 3DMark CPU profile scores at stock. Here are the AIDA64 memory benchmark scores at stock. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4346 MHz with 0.988 volts. The average CPU temperature is 77.5 degrees Celsius. The average CPU package power is 181.4 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 4836 MHz with 1.083 volts. The average CPU temperature is 81.5 degrees Celsius. The average CPU package power is 196.8 watts. Of course, we can increase the maximum power limit by using Precision Boost Overdrive. And that's exactly what we'll do in our very first overclocking strategy. But before that, make sure to locate the Clear CMOS button. Pressing the Clear CMOS button will reset all your BIOS settings to default, which is very helpful if you want to start your BIOS configuration from scratch. In our first overclocking strategy, we simply leverage Precision Boost Overdrive and AMD EXPO. With the launch of Zen 5, AMD introduced an improved version of their Precision Boost Overdrive Overclockers toolkit. This toolkit allows us to fine-tune some of the parameters governing the Precision Boost frequency boosting algorithm. The Precision Boost Overdrive 2 toolkit for Zen 5 Ryzen processors includes the overclocking knobs from Zen Plus, PPT, TDC and EDC, Zen 2, Boost Override and Scalar, Zen 3, Curve Optimizer, and the newly announced Curve Shaper for Zen 5. There are 3 levels of Precision Boost Overdrive. In this overclocking strategy, we're just enabling Precision Boost Overdrive, whereas in the following strategies, we'll explore tuning the parameters. Increasing the PPT and to a lesser extent the TDC and EDC limit will help unleash the frequency in multi-threaded workloads previously limited by the PPT. EXPO stands for AMD Extended Profiles for Overclocking. It's an AMD technology that enables ubiquitous memory overclocking for AMD platforms supporting DDR5 memory. EXPO allows memory vendors, such as G.Skill, to program higher performance settings onto the memory sticks. If the motherboard supports EXPO, you can enable higher performance with a single BIOS setting, so it saves you from a lot of manual configuration. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO 2. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Enabled, then save and exit the BIOS. After applying the BIOS settings, the boost frequency at one active thread is about 5,531 MHz, and the average boost frequency gradually trails off to 5,046 MHz when all cores are active. In a light, single-threaded workloads, all but one core in CCD0 can boost to over 5.7 GHz, and all cores in CCD1 boost over 5.5 GHz. We reran the benchmarks and checked the performance increase compared to the default operation. As we typically see with the high-end SKUs of a product line, the performance is restricted by the power limits. By enabling PBO, we can add about 40% extra power budget in an all-core workload. Combined with enabling higher memory speeds, that translates into pretty decent performance gains across the board. The GeoMean benchmark performance improvement is plus 4%, and we get a maximum improvement of plus 14.98% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4,706 MHz with 1.057 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 242.3 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5,019 MHz with 1.125 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 241.6 watts. In our second overclocking strategy, we fine-tune some of the precision boost parameters using PBO, and we undervolt using Curve Optimizer. Fused maximum frequency, or Fmax, is one of the performance limiters governing the Precision Boost 2 algorithm. Basically, it determines the maximum allowed frequency for the cores inside your CPU. For dual CCD processors like the Ryzen 9 9950X, each CCD will have its own Fmax. For the Ryzen 9 9950X, CCD0 has an Fmax of 5.75 GHz, whereas CCD1 has an Fmax of 5.45 GHz. Boost Clock Override, or Fmax Override, is one of the tools available in the PBO2 Overclockers toolkit. It allows the user to override the arbitrary clock frequency limit between minus 1000 MHz and plus 200 MHz in steps of 25 MHz. It's important to note that the Fmax override only adjusts the upper ceiling of the frequency and doesn't act as a frequency offset. Ultimately, the Precision Boost 2 algorithm still determines the actual operating frequency. With a plus 200 Fmax boost override, the new maximum boost frequency for the Ryzen 9 9950X is 5,950 MHz for CCD0 and 5,650 MHz for CCD1. Scalar is a tool that allows us to override the warranted silicon stress level, or FIT. You can adjust the maximum allowed FIT level to 10 times higher than the factory fused limit. The effect of increasing scalar is that the Precision Boost algorithm more aggressively pursues higher voltages, as it is less concerned with CPU lifespan. For Zen 5 CPUs, it appears that scalar is making a comeback because these CPUs are very voltage limited. The programmed vid limit is 1.4 volt, though we see slight excursions above that in really light single-threaded workloads. When all 16 cores are active, the maximum voltage is 1.345 volt. The programmed FIT value of this particular Ryzen 9 9950X is 6838.1. So with a 10x scalar, the new FIT value is 68,381. We find that in an all-core workload, the maximum voltage increased from 1.345 volt to 1.37 volt. That's not a big increase, but in voltage-constrained scenarios, every little bit helps. Curve Optimizer is probably the most well-known tool of the PBO Overclockers toolkit. It is most commonly known for its undervolting capabilities, but on AMD Ryzen CPUs, it kind of also works as an overclocking tool. Let me explain, and let's start with the voltage frequency curve. Simply put, a voltage frequency curve describes the relationship between an operating frequency and the voltage required to operate at that frequency. Every modern SoC has a factory-fused voltage frequency curve and uses this to dynamically adjust the power consumption depending on the workload needs. Here's the default voltage frequency curve of my Ryzen 9 9950X processor. You'll notice that there are in fact two VF curves. That's because the Ryzen 9 9950X has two CCDs of quite different quality. We can immediately make a simple and redundant observation. The higher the frequency, the higher the voltage we need. For example, CCD0 requires only 1.1 volt for 4925 MHz. However, we need over 1.25 volt for 5475 MHz. This rule also applies to CCD1. 1.1 volt gets us 4.65 GHz, whereas we need 1.25 volt for 5200 MHz. I must make an important side note here. The native VF curve for CCD1 is not as bad as it is portrayed in this chart. Instead, it is the effect of the CCDs sharing the same voltage rail and having linked Fmax frequencies. If we disable CCD0 and reassess the VF curve of CCD1, we find that CCD1 is able to run the high frequencies at much lower voltages. At 5.3 GHz, we even need about 100 mV less. Of course, CCD1 is still not at the same level as CCD0. We also notice that the maximum allowed voltage is 1.35 volt when all cores are active. We can increase this to 1.375 volt by setting a 10x scalar. The Precision Boost 2 algorithm utilizes the VF curve to find what's the maximum allowed frequency at 1.375 volt. With the default curve, that's 5600 MHz for CCD0 and 5450 MHz for CCD1. However, as I showed a little earlier, we can use the Fmax Boost Override tool to increase the Fmax limit by another 200 MHz. If we set a negative curve optimizer, we can shift the entire voltage frequency curve along the voltage axis, and suddenly we need a lot less voltage for every operating frequency. For example, for 5 GHz we needed about 1.11 volt on CCD0 and 1.175 volt on CCD1. But with a negative curve optimizer, now we only need 1.066 volt on CCD0 and 1.12 volt on CCD1. Moreover, the frequency is also boosting higher. The highest frequency with all 16 cores active has increased by 100 MHz from 5630 MHz to 5730 MHz on CCD0. These higher frequencies are now possible because our curve optimizer undervolting pulled them below the 1.375 volt threshold. Curve Optimizer is a very powerful tuning tool. It's simple, but not simplistic. And the more you dig into how it works, the more intricate it becomes to apply to your system and to squeeze more performance out of your system. Most commonly, we would set a negative curve optimizer, and it helps in two ways. First, undervolting lowers the operating voltage, temperature, and power consumption. Second, as a consequence, the Precision Boost 2 algorithm can leverage the additional headroom to boost to higher frequencies. So you tend to get lower temperatures and higher performance. It's a win-win. However, there are a couple of caveats when it comes to using Curve Optimizer. Curve Optimizer impacts the entire voltage frequency curve, so it affects stability across the entire range of operating frequencies, from 600 to 6000 MHz. The same Curve Optimizer value also impacts differently across the curve. Of course, having a CPU with two CCDs, which each have their own VF curve, makes the tuning process a lot less straightforward than CPUs that just have a single CCD. The manual tuning process for Curve Optimizer can become quite convoluted because it spans a very wide range of workloads, going from light single-threaded workloads all the way to heavy all-core workloads. Furthermore, on a dual CCD chip, we also have to tune two VF curves at the same time. I want to emphasize something specifically about stress testing for Curve Optimizer, because I often see comments on my videos of people saying, I thought my Curve Optimizer was stable, but then I played some games and now it wasn't stable. It's a very common mistake to exclusively rely on all-core heavy stress tests like OCCT or Prime 95 to test your Curve Optimizer setting, because those applications only test very specific parts of your VFT curve. Typically, it tests the part where the voltage is relatively low, the frequency is medium, and the temperature is very high. But your games don't run at those VF points. Your games typically run at moderate temperatures and at higher frequencies. So you need to use other applications to tune for those scenarios. To better illustrate my point, here are the final VF curves of this overclocking strategy. I'll add the voltage frequency points during three workloads: Final Fantasy 15, OCCT AVX2 CPU stress test, and Y-Cruncher BKT. You can see not only do the points diverge significantly from the VF curve, but they're also at totally different parts of the curve. The average frequency voltage temperature during Final Fantasy 15 is 5.5 GHz with 1.34 volt at 69 degrees Celsius. In contrast, the OCCT AVX2 stress test runs at 4.8 GHz with 1.03 volt at 95 degrees Celsius. Obviously, we cannot verify game stability by running this stress test. Furthermore, although the Y-Cruncher BKT also runs at 95 degrees Celsius, it's at much higher frequency than the OCCT workload and thus stress tests a totally different part of the VF curve. I find that the easiest way to approach Curve Optimizer is by first finding the weak part of the curve, and that can change architecture to architecture and chip to chip. I found that in this case, the Y-Cruncher BKT workload was the first one to become unstable when I was doing curve optimization. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO 2. Switch to the Advanced menu. Enter the AMD Overclocking submenu and click Accept. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Set Precision Boost Overdrive Scalar Control to Manual. Set Precision Boost Overdrive Scalar to 10x. Set CPU Boost Clock Override to Enabled Positive. Set Max CPU Boost Clock Override to 200. Enter the Curve Optimizer submenu. Set Curve Optimizer to Per CCD. Set CCD0 Curve Optimizer sign to negative. Set CCD0 Curve Optimizer magnitude to 15. Set CCD1 Curve Optimizer sign to negative. Set CCD1 Curve Optimizer magnitude to 10. Then save and exit the BIOS. After applying the BIOS settings, the boost frequency at one active thread is about 5,582 MHz, and the average boost frequency gradually trails off to 5,204 MHz when all cores are active. In a light single-threaded workload, all cores in CCD0 can boost to over 5.8 GHz, and all cores in CCD1 boost to over 5.6 GHz. We reran the benchmarks and checked the performance increase compared to the default operation. By adjusting the Fmax boost override, scalar, and curve optimizer, we both undervolt and overclock both CCDs of this Ryzen 9 9950X. The performance improvement is noticeable, especially in multi-threaded workloads. However, we also get a small performance uplift in single-threaded workloads. The GMean benchmark performance is plus 5.15%, and we get a maximum improvement of plus 16.54% in the AI benchmark. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4,844 MHz with 1.041 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 242.5 watts. When running the OCCT CPU SSE stability test, The average CPU core effective clock is 5137 MHz with 1.117 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 242.1 watts. In our third overclocking strategy, we tune the memory subsystem performance. Seasoned AMD Ryzen overclockers will know very well that there are essentially three parts of our memory subsystem: in the Infinity Fabric, the memory controller, and the system memory. They're more commonly referred to as the F-clock, the U-clock, and the M-clock. In the past, these would all be tightly coupled together, but on modern Ryzen CPUs, like the Ryzen 9 9950X, we can tune all of these independent. I had three objectives when it comes to tuning the memory subsystem performance. I want to increase the F-clock as high as possible, I want to run the U-clock and M-clock in sync, and I want to tighten up the memory timings. The fabric frequency, or F-clock, is generated by the SoC PLL, derived from a 100 MHz reference clock input. The reference clock is multiplied by the F-clock ratio, which you can configure in the BIOS. The standard operating frequency of the Infinity Fabric is 1800 MHz, but on many motherboards, you'll find it runs 2100 MHz when Precision Boost Overdrive is enabled. That said, it doesn't seem there's much overclocking headroom beyond 2100 MHz. I managed to set it to 2200 MHz and it booted up. However, it was not stable across the entire benchmark suite, not even with voltage adjustments. Speaking of voltage, the Infinity Fabric voltage is provided by the VDDG voltage supply, derived via an integrated voltage regulator from the VDDCR miscellaneous voltage rail. AMD Granite Ridge has two DDR5 Unified Memory Controllers, or UMC in short, and each provides two 32-bit memory channels. The memory controllers are located in the I/O die and are identical to the memory controllers on the Ryzen 7000 Rafael processors. Note that the Ryzen 8000 Hawkpoint processors actually have a newer memory controller. The Unified Memory Controller Frequency, or U-clock, is derived from the UMC clock, one of the SoC PLLs. The memory controller frequency is tied directly to the system memory frequency. It can run either at the same or half its frequency. At default, the memory controller runs at the same frequency as the system memory at 2400 MHz. However, we find that when enabling EXPO, often the motherboard auto rules will drop the memory controller frequency to half the memory frequency. We can easily force the memory controller to run at the same frequency as the system memory by setting uclock div1 mode to uclock equals memclock. It is also suggested to enable SoC Uncore OC mode to disable all power saving technologies affecting the clock frequencies of the memory subsystem. The VDDCR SoC voltage rail provides the external power for multiple internal voltage regulators on the SoC for the various IP blocks, including the memory controller. The VDD-IO MEM voltage rail is related as well, as it provides the external power for the VDDP DDR5 bus signaling. The last piece of the puzzle is to tune the memory timings, and for that I rely in part on the ASUS memory presets technology and in part on experiences from previous SkatterBencher guides. ASUS memory presets is an ASUS overclocking technology that provides a selection of memory tuning presets for specific memory ICs. The presets will adjust the memory timings and voltages. The ROG Crosshair X670 eHero motherboard sports 14 memory profiles for a variety of memory ICs and configurations. Since we're interested in simply adjusting the memory timings, we can try the Hynix 6400 1.4 2x16GB single rank preset. Note that I stick with the EXPO primary timings and only leverage the memory preset for the secondary and tertiary subtimings. The kit can pass the benchmarks at DDR5 6400, but it's not stable enough to pass the OCCT memory stability tests. However, we passed the OCCT memory stability test by reducing the memory frequency by one notch to DDR5 6200. After the tuning, our AIDA64 performance improves significantly. We got about plus 35% extra performance by enabling EXPO and added another 10% on top of that by tuning the memory timings. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI overclock tuner to EXPO 2. Set memory frequency to DDR5 6200. Enter the DRAM timing control submenu. Enter the memory presets submenu. Select load Hynix 6400 1.4 volt 2x16GB single rank and click OK. Leave the memory presets submenu. Set TCL, TRCCD and TRAS according to the EXPO kit. Set TRAS to 38. Leave the DRAM timing control submenu. Switch to the advanced menu. Enter the AMD overclocking submenu and click Accept. Enter the DDR and Infinity Fabric frequency timings submenu. Enter the Infinity Fabric frequency and dividers submenu. Set Infinity Fabric frequency and dividers to 2100. Set uClock div1 mode to uClock equals memclock. Leave the Infinity Fabric frequency and dividers submenu. Leave the DDR and Infinity Fabric frequency timings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Set Precision Boost Overdrive Scalar control to Manual. Set Precision Boost Overdrive Scalar to 10x. Set CPU Boost Clock Override to Enabled Positive. Set Max CPU Boost Clock Override to 200. Enter the Curve Optimizer submenu. Set Curve Optimizer to per CCD. Set CCD0 and CCD1 Curve Optimizer sign to negative. Set CCD0 Curve Optimizer magnitude to 15. Set CCD1 Curve Optimizer magnitude to 10. Leave the Curve Optimizer submenu. Leave the Precision Boost Overdrive submenu. Enter the SLC Encore OC mode submenu. Set SLC Encore OC mode to Enabled. Leave the SLC Encore OC mode submenu. Enter the SLC voltage submenu. Set SLC voltage to 1300. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. We know from previous Ryzen 9000 overclocking guides that memory subtiming tuning can have a substantial impact on performance. And that's no different with the Ryzen 9 9950X, even though the performance uplift is less outspoken. We get a satisfactory performance uplift across the board. The GeoMean benchmark performance improvement is plus 6.49%, and we get a maximum improvement of plus 38.66% in PY prime. In our fourth and final overclocking strategy, we take advantage of Curve Shaper to try and squeeze more performance out of our CPU. Curve Shaper is the newly announced tool in the Precision Boost Overdrive Overclockers toolkit that was introduced alongside Zen 5. I already had a look at the tool in a different video on this channel, so check out that video if you want to have more information on how it works. In theory, it seems Curve Shaper is pretty straightforward. You get 15 additional tunable points across the VF curve. But the devil is in the details, because AMD's Precision Boost 2 technology doesn't really work with VF points. So instead of getting a list of specific tunable VF points, we get 5 regions and 3 temperatures. The regions have a bit of a vague terminology and are not clearly defined. I will get back to that in a minute. The temperature points are more straightforward as they're defined as -5, 50 and 90 degrees Celsius. The idea of Curve Shaper is that you can fine-tune your CPU's VFT curve in much more specific areas than with Curve Optimizer. I've already shown how effective the tool is when we use overclocking strategies with asynchronous E-clock. And I've also shown it can be very helpful if you have a scenario where your operating temperature ranges from -50 all the way to plus 90 degrees Celsius. For this video, I wanted to achieve 2 things. First, I want to illustrate how Curve Shaper works in tandem with Curve Optimizer. And 2, I want to check if there are performance improvements opportunities in more specific load or temperature scenarios. So as the basis for this overclocking strategy, I rely on the settings from OC strategy number 3 with Curve Optimizer set to -15 for CCD0 and -10 for CCD1. Then I try setting the Curve Shaper for medium temperatures to -5, starting with maximum frequency. This setting further undervolts the CPU in idle and light load scenarios. Unfortunately, it wasn't stable. I also tried setting the medium and high frequency medium temperature to negative values, but that wasn't stable either. Then I try the same for the high temperatures to see if there's any frequency margin under full load conditions. Here I found that there's enough margin to set a -5 curve shaper. In theory, this should give us a little more performance in high load scenarios. To illustrate how curve shaper builds on top of curve optimizer, I want to share two VF curves. In the first graph, we compare the curves from OC strategy number 2 and 4 by using my standard methodology. The methodology relies on using the OCCT memory stress test to keep the cores fully active. However, the temperature is only about 50 degrees Celsius. We can see there's only a slight shift in the curve. In the second graph, we compare the curves using the Y-Cruncher BKT workload. This workload is relatively light as it doesn't push the CPU to its TJ max. However, the operating temperature is around 80 degrees Celsius. We can see pretty much the same. So the key takeaway is that with the high temperature curve shaper, we're getting more undervolt at the hotter parts of the VFD curve. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO 2. Set memory frequency to DDR5 6200. Enter the DRAM timing control submenu. Enter the memory presets submenu. Select Load Hynix 6400 1.4 volt 2x16 GB single rank and click OK. Leave the memory presets submenu. Set TCL, TRCCD and TRAS according to the EXPO kit. Set TRAS to 38. Leave the DRAM timing control submenu. Switch to the advanced menu. Enter the AMD overclocking submenu and click Accept. Enter the DDR and Infinity Fabric Frequency Timings submenu. Enter the Infinity Fabric Frequency and Dividers submenu. Set Infinity Fabric Frequency and Dividers to 2100. Set uClock Div 1 mode to uClock equals memclock. Leave the Infinity Fabric Frequency and Dividers submenu. Leave the DDR and Infinity Fabric Frequency Timings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to motherboard. Set Precision Boost Overdrive Scalar control to manual. Set Precision Boost Overdrive Scalar to 10x. Set CPU Boost Clock Override to enabled positive. Set Max CPU Boost Clock Override to 200. Enter the Curve Optimizer submenu. Set Curve Optimizer to all cores. Set CCD0 and CCD1 Curve Optimizer sign to negative. Set CCD0 Curve Optimizer magnitude to 15. Set CCD1 Curve Optimizer magnitude to 10. Leave the Curve Optimizer submenu. Enter the Curve Shaper submenu. For medium, high, and maximum frequency, set High Temperature to Enable. For medium, high, and maximum frequency, set Temperature Signs to negative. For medium, high, and maximum frequency, set Temperature Magnitudes to 5. Leave the Curve Shaper submenu. Leave the Precision Boost Overdrive submenu. Enter the SoC Encore OC mode submenu. Set SoC Encore OC mode to enabled. Leave the SoC Encore OC mode submenu. Enter the SoC voltage submenu. Set SoC voltage to 1300. Then save and exit the BIOS. After applying the BIOS settings, the boost frequency at one active thread is about 5602 MHz, and the average boost frequency gradually trails off to 5269 MHz when all cores are active. In a light, single-threaded workload, all cores in CCD0 can boost to over 5.8 GHz, and all cores in CCD1 boost over 5.6 GHz. We reran the benchmarks and checked the performance increase compared to the default operation. Curve Shaper is definitely a matter of fine-tuning the margins of the CPU. However, the performance uplift is surprisingly consistent across all workloads. The geomean benchmark performance improvement is plus 7.06%, and we get a maximum improvement of plus 37.81% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4885 MHz with 1.026 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 236.3 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5166 MHz with 1.099 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 236.6 watts. Alright, let's wrap this up. This is my third Ryzen 9000 overclocking guide, and I finally got to play with the dual CCD Ryzen 9000 CPUs. Dual CCD CPUs are always interesting to overclock because we're essentially overclocking two VFT curves. The ingredients for a successful Ryzen 9000 overclock are the same as with the single CCD CPUs. You enable PBO for more power, you enable EXPO for faster memory, and then you undervolt using Curve Optimizer. And that will give you pretty much the most performance gains that you can get out of your CPU. Adjusting the memory timings also helped with the 9950X, but I feel like the performance uplift wasn't as big as what we saw with the 9700X and the 9600X. One of the key performance limiters that I didn't discuss in this video is the Fmax limiter. That limiter essentially sets the maximum allowed frequency at very high operating temperatures, and for the 9950X, that's 5375 MHz. I'm going to discuss this one in a follow-up video to this overclocking guide. Anyway, that's all for today. I want to thank you for watching and the patrons for the support. As per usual, there will be a written version of this video up on my blog if you want to read through everything. If you have any questions or comments, drop them in the comment section below, and see you next time.